Please start.
Okay, sorry for the inconvenience. Hi, my name is Nicholas Wehner and I'm a PhD student from the University of Würzburg. This is a joint work with my colleagues from University of Würzburg, Michael Seufert, Joshua Schüler, and our head of chair, Tobias Hosfeld, as well as with my colleagues from Austrian Institute of Technology in Vienna, Sarah Wassermann and Peter Casas. Today, I present machine learning techniques for estimating WebQE from encrypted network traffic. First, I will give a short motivation why the topic is of interest at all. Then I will introduce the testbed for our data measurements and present the methodology we use for predicting WebQE. And this includes also the feature extraction process as well as the tested models. Finally, I will present the results. So what happens every day in the internet is that a user requests a network service over the internet, for example, a web page request. And the internet service provider plays here a crucial role as the ISP is often responsible or blamed for a bad service performance. To quantify the service performance, we usually use the concepts of quality of service and quality of experience. And today we focus on the inference from QE based on QS. So in particular for web browsing QE, research has shown that loading times are the most important influence factor. And in order to avoid expensive studies, several metrics have already been proposed to approximate WebQE. Prominent metrics here are, for example, the page load time, so the time until a document has been fully loaded, and the speed index, which considers the visual progress on the viewport over time for its computation. The problem with the speed index is that the computation is very expensive as video frames have to be compared one by one. Thus, a more computational efficient approximation of the speed index has been developed, which depends on specific paint objects only, and this is called the Real User Monitoring Speed Index, short RUMC. To avoid low QE and thus end-user frustration and churning and subsequently revenue losses, the ISP should thus be interested to implement a QE monitoring. However, as the trend goes towards encrypted traffic more and more, this task becomes also more and more difficult, as it's no longer possible to directly estimate the WebQE from the application layer data, but instead it's required to estimate WebQE from network layer data, so from QS. And one potential solution to this problem is the usage of machine learning. The data measurements for our analysis were performed with a testbed using Web Page Test, which is an open source web performance monitoring tool. Our testbed is depicted here and consisted of 3 different devices, which were connected to the internet through an additional computer each. These additional computers served as network emulator using the Linux tool TC, and they also captured the network traces with TCP dump. With the web page test agents and our custom web page test server instance, we could then extract about 90 different key performance indicators and also the WebQE metrics such as page load time or RUMC. We then accessed the Alexa top 500 pages for 10 times with each device and with the same access network setups. Our access network setups included shapings in different scenarios, for example, transmission delays, packet loss rates, and also bandwidth limitations. And for this work, we focused only on the runs without shaping and with different packet loss rates. Based on these monitored network traces and our WebQE ground truth, we then used supervised learning to estimate the RUMC from the network traces. For supervised learning, the first thing we did was to slot the network traces into 100 millisecond windows to allow a real-time temporal granularity. So in the end, we obtain time series data, which characterizes a web page load. Our extracted feature set then included count-based features, for example, the amount of transferred bytes, time-based features like the packet inter-arrival times, and also distribution-based features. All these features were computed for the total traffic, the uplink traffic, and the downlink traffic each. And then we also computed the same features explicitly for the 3 IP addresses with the highest exchange data volumes. So we assumed that most web pages communicate mainly with a few servers only, and this would enable a reduction of the feature set in the future. Additionally, we also computed the same features for varying subnets of these top IP addresses to accommodate for multiple IP addresses originating from the same subnet. We computed these features once for the current window, which we call window features, and also for the whole session up to the current window, which we call the session features. And this feature extraction resulted in 1,979 features in total. For this work, we investigated around 60,000 web page loads, which were created during November 2019. For the prediction of the Ramsey, several different models were tested. So first I will present the used regression models. We applied the well-known regression models like linear regression, decision tree regression, and also ensemble methods like random forest or extreme gradient boost to our data using scikit-learn. These models were also optimized using grid search. As a second approach, we used a simple neural network regressor with 3 hidden layers to estimate the Ramsey directly. And finally, we used recurrent neural networks. And for these networks, we used either LSTM or crew cells for the layers, as they provide multiple benefits compared to normal recurrent neural networks. So for the first two approaches, we used only the final session-based features of the last window as input, as these features summarize the complete session of a web page load. And for the recurrent neural networks, we used then all features of all windows as input. As a complementary approach to the regression models, we also designed a binary classification approach, again using recurrent neural networks. Here, the time series features are again fed into the recurrent neural network step by step. This time, however, the Ramsey is mapped to a binary variable beforehand, and this variable indicates whether the Ramsey is already loaded or not, and 0 represents that the Ramsey has not been loaded yet, and a 1 represents that it's loaded. So the model then predicts for each window whether the Ramsey is loaded or not. And for example, here for window I+1, the Ramsey would be considered loaded. After these binary predictions, we can then aggregate these predictions and thus approximate the real Ramsey value. The problem here, or it's only a minor problem as we will see later, is that this introduces an additional error as we do not know when exactly the Ramsey was loaded in the previous window. On the other hand, the binary mapping also provides the benefit that the training targets become more balanced, and this may allow a more efficient training and in the end also a better model. So let's look at the results for the regression models first. For all our evaluations, we split the data into training, validation, and test set in a way that each website was present in all sets. And we can here see in the figure the CDFs for the obtained prediction errors per model. The x-axis denotes the prediction error, so the error between prediction and ground truth in seconds. And it is visible that especially the ensemble methods, so random forest and extreme gradient boost, show the best results regarding the scikit-learn models. And this is not surprising, it comes as expected, as ensemble models have proven to be working well for QE predictions. However, when considering the recurrent neural network regression with LSTM layers, we can see that it performs better. So next we consider only the recurrent neural network approaches. Again, we have a CDF, an error CDF for the predictions. And for both the CRU and the LSTM layers, the binary classification approach, which is depicted with the dotted lines, shows better results than the regression models, which are depicted with dashed lines. For example, for the LSTM regression, the median absolute error is around 0.29 seconds, while for the classification approach, the median absolute error is only 0.21 seconds. And even the error which is introduced with the binary mapping, which is visible in the differences between the dotted and solid lines, is only marginal and doesn't affect the performance very much. So when comparing the layers for the recurrent models, the LSTM performs slightly better. However, the difference is negligible. An additional benefit of this many-to-many prediction is that you can get basically real-time predictions with a delay of 100 milliseconds, and thus much faster insights than with the regression approaches where you have to wait until the end of the session. So finally, we evaluated also several feature subsets to analyze the feature importance. You can see here in the table the mean squared error, the mean absolute error, the median absolute error for the different feature subsets and recurrent layers for the binary classification task. We can see here that there are no large differences between the feature subsets and that it is basically possible to obtain good results with the top 3 IP addresses only. They are denoted with the top W or top S. So summarizing, a custom testbed for performing WebQE measurements in encrypted network traffic has been presented. It was shown that it is possible to accurately predict the Ramsey on both session level and window level with regression and classification methods. And future works include an evaluation of the models on a more diverse data set. Of course, there are also additional WebQE metrics like page load time or above the fold, which are worth to consider in the future. And at the moment, the current feature dimension is much too large for a reasonable in the field application. So a reduction of the feature dimension is required too. And besides the presented models, it would also be interesting to test more sophisticated models, for example, temporal convolutional networks or also recurrent neural networks with attention mechanisms. And finally, to obtain more fine-grained models, a clustering of web page families beforehand could be beneficial, where a web page family is, for example, a family of news pages or messaging pages or also video portals, so pages which behave similar in general in terms of network traffic. This concludes my talk, and thanks for your attention.
Thanks, Nicholas. Very interesting talk. Is there any question? Again, I repeat, for the question, just open your mic. Don't worry, or if you don't have a mic, just write in the chats of the question. Well, I have a question actually. Can you give more details on how you perform the tuning of the parameters for the different algorithms? Because you say you had the validation set, but can you please provide more details about the hyperparameter tuning for the final best algorithm that you choose?
Yeah, so for scikit-learn, we used the grid search where we proposed different parameters, for example, the number of trees for random forests or whatever. And for the neural network approaches, we did a trial and error. So we did not do anything like Bayesian optimization or something like this. This was more like trial and error, but we looked at the number, so the size of the networks are comparable. It's not like one network had much more neurons than the other one, and yeah.
Okay, but so did you like also study the number of layers, the input and the sizes, or you just took like some?
So for the neural networks, the number of layers and the sizes, so the number of neurons were identical.
Oh, okay, but my question is, did you tune also these or not?
No, just by trial and error, more or less. So I checked the training validation loss, and looked if there is more capacity. So if I saw that the training and validation loss deviated strongly, I increased the capacity for both models. And yeah.
Okay. Okay, thanks for the answer. Are there a question for Nicolas? If not, thank you a lot for the presentation, and